So let's check this out. This is called the triple point of tert-butyl alcohol. It's going to occur under conditions we can't recreate here. And we require a vacuum chamber, which we don't have, or a vacuum flask, which we don't have. But we can at least watch what's going on here. If you remove the pressure enough, this alcohol begins to boil. But it's also got a pretty high freezing point. So after a while, we can get it to freeze. So under these low pressure conditions, atmospheric pressure is low enough that it boils. And we do this for 30 seconds, you can see on the screen. And then as the temperature drops and the kinetic energy starts to slow down, the boiling stops. Now, this thing called triple point is pretty neat because we're going to see solid, liquid, and gas phases all at the same time. And pay attention right here because this is as the water is freezing, the tert-butyl alcohol is freezing. And the pressure is still low, so now it is also boiling. And of course, over here, it is still at a liquid phase. So what you're seeing is a particular set of conditions where all three states of matter can exist at one time. Pretty cool. So how do we get to this set of conditions where all three states of matter can exist at once? We're going to look at something called a phase diagram. It looks like this. Sorry. It looks like this. And let's bring this up here a little bit so we can see better what's going on. So here's what a phase diagram is telling us. Notice that we have temperature on the x-axis and we have pressure in atmospheres on the y-axis. And we want to be paying attention to some pretty important points here. Obviously, you're interested in the triple point, but we'll get to that. So notice that pressure is starting at the origin of 0, and our temperature in degrees Celsius is obviously way down here. Notice that 0 for Celsius is right here. So of course negative 273 degrees Celsius is our temperature in kelvins, which is of course 0 Kelvin. So we're at the origin. Here's how we read this. Let's say that we're at 0 degrees Kelvin on our temperature scale, so our molecular motion is nil. And let's say that we're going to increase the temperature from the origin where the pressure is still 0. And notice that even though the temperature is starting to increase from 0 kelvins, with no pressure, there's nothing to hold the molecules together, and our state of matter, this is of course a triple point diagram for water, our state of matter is still in the steam phase no matter what our temperature is. If it's 0 kelvins, if it's 0 degrees Celsius, our water is still steam. It never coalesces into the liquid phase. If we start at 0 degrees Kelvin with 0 molecular motion and increase the pressure from 0 degrees Kelvin, notice that it starts in the ice phase and never gets out. It never goes to liquid. It never goes to gas. Here we have 1 atmosphere, what we'll call atmospheric pressure, obviously, standard atmospheric pressure. Here we have 0 degrees Celsius, right at the border of the freezing temperature. So let's zoom in a bit here. Let's say that we start at 0 degrees Celsius and we begin to increase the pressure from 0 atmospheres. Notice that even at 0 degrees Celsius, which water should be freezing, at 0 degrees Celsius and 0 atmospheres, our water is in the vapor phase. But as the pressure increases and starts to smash those molecules together, notice that it hits the interface of ice first. Water is one of the only substances that we know that does this, where it doesn't go from the gas phase to the liquid phase to the solid phase at a constant temperature, it goes to the solid phase first. And that's because water is one of the few substances that is less dense when it is a solid than it is as a liquid. If we continue on and keep increasing our pressure at 1 atmosphere, standard atmospheric pressure, water finally reaches the interface between water and ice. And if we continue to increase the pressure, water eventually at 0 degrees Celsius will remain in the liquid phase, even though it is still at 0 degrees Celsius. Pretty neat. If we are at 1 atmosphere and 0 degrees Kelvin, obviously our water is ice. But as we continue to increase the temperature at 1 atmosphere, here at 0 degrees Celsius is where we see the interface between the solid and liquid phases. As we continue to increase the temperature at 1 atmosphere, now we enter the interface between the liquid and steam phases. And of course, if we continue to increase the temperature at a standard pressure of 1 atmosphere, of course, our water boils and is now in the steam phase. We're interested in a couple of points here. Let's zoom in on this one called critical point. Critical point gives us 2 terms that we want to keep in mind. We'll call this PC. Let me make my ink a little narrower so you can read it. We'll call PC, I don't know why my pen isn't writing. Thank you. We'll call PC critical pressure. Remember that pressure is on the y-axis. Once we exceed this critical pressure, this line here, there is no temperature at which we can heat this. Remember that we have the critical pressures on the y-axis, this line. If we exceed critical pressure, there is no temperature that we can increase that will bring our substance out of the liquid phase. So once we exceed critical pressure, once we exceed this, the pressure is so great that the substance remains a liquid no matter what the temperature is. So at critical pressure, the substance remains a liquid regardless of temperature. This critical point is also what we're going to call the critical temperature. We'll call this TC. This is called critical temperature. Remember that our temperature is on the x-axis, so we are here. At critical temperature, no matter what pressure we exert, once we are beyond critical temperature, no amount of pressure can revert our substance to liquid. So at critical temperature, no matter what our pressure is, so critical temperature, we are on the x-axis, we can, once we're beyond this, no matter what pressure we exert, we cannot get this into a liquid phase. And any set of conditions here is what we call a supercritical fluid. Notice that it's kind of a strange situation here. It's not a liquid, it's not a gas, it's not a plasma either, but it's kind of existing simultaneously. That brings us to this thing called the triple point. Let's zoom out. At the triple point, which is a temperature slightly higher than 0 degrees Celsius and at a pressure of 0.06 atmospheres, this is where our substance is at all 3 phases. And a lot of times they just abbreviate P3, the triple point. So at this situation, the substances is all 3 states of matter at the same time. So looking at this for water, if we start at 0.06 atmospheres and 0 Kelvin in the ice phase. As we continue on at 0.06 atmospheres and increase our temperature gradually, at 0 degrees Celsius, we're still in the ice phase, but because our pressure is so low, it's not going to, water has to shrink in density or it's got to increase its density. It's got to shrink a little bit to go to the liquid phase, because liquid is more dense than the solid. And of course, the pressure just isn't sufficient for that. So we're still in the ice phase, even as we increase the temperature beyond 0 degrees Celsius. And here is where water exists in all three phases. It's a very delicate balance, but pretty neat when you see it in action. I should mention that water is one of the few substances that does this, and that means that this interface between the ice and the water phase kind of tilts backwards like this, because water remains ice at a lower pressure than it goes to water. Other phase diagrams don't look like this. This is a much more standard phase diagram. Remember that this is the ice phase, this guy here. Sorry, I'm trying to erase. Trying to change ink. Hang on, let me smack this with my big beat stick. Hang on. So this is the solid phase. This is the liquid phase. And this is the gas phase. And when we see this makes a lot more sense, that when we start from say 0 atmospheres and 0 kelvins, as we increase, so say this is 0 degrees Celsius or whatever, this is the normal freezing point. As we increase our pressure, our gas condenses to a liquid and then finally to a solid, which is what we would normally expect. As we start here at our normal 0 degrees Kelvin, but at 1 atmosphere, and we move this way, we notice that it's a solid because we're 0 degrees Kelvin, so of course it should be a solid. As we continue to increase our pressure, increase our temperature, it boils off here. Now it's in the liquid phase, and as we continue, it enters the vapor phase. And this is normally what we should expect with any normal acting substance. So water is pretty weird. All right, enjoy. I'll see you later.